Good morning. So, our today's topic of discussion will be normal density and discriminant function. So, in the last class we have talked about different types of classifiers which were actually derived from a Bayes classifier called Bayes minimum risk classifier, and in Bayes minimum risk classifier we said that I have to have a number of functional units which will compute the risk involved for taking any particular action. So, the risk function that we said was of this form, R of alpha I given x, that means given a feature vector x, the risk involved in taking an action alpha I, which was of this form lambda alpha I given omega j into p omega j given x, take the summation for j is equal to 1 to c, where c is the total number of classes. Okay. So, for each action alpha I, when I have say p number of actions in my system, then there will be p number of such risk functions computed, and that corresponding action alpha will be taken for which this risk function is minimum. So, that is what is Bayes minimum risk classifier. And then we have said that we can derive another classifier which is minimum error rate classifier from this Bayes minimum risk classifier, where this risk function we have said that it can be reduced in the form of 1 minus p omega I given x. Okay. So, when this is minimum, the corresponding we have to put x in the corresponding class omega I. Okay. And as this has to be minimum, correspondingly what we get is this probability p omega I given x, that has to be maximum. So, this is nothing but the basic classification rule that we discussed about when I started talking about Bayes decision theory, that if p of omega I given x is greater than p of omega j given x for all j not equal to I. Okay. So, this is what is the a posteriori probability, that given a feature vector x, what is the probability that x will belong to class omega I, and this is what is the probability that x will belong to class omega j. So, for that particular omega I, where p of omega I given x is maximum, we have to put or we have to classify x as belonging to that particular class. Okay. Then we have talked about the discriminant functions. So, there what we said is for every class I or every omega I, for I varying from 1 to c, as we are considering a generalized case, that as if we have c number of classes. So, for every class we define a function say g I x. Okay. So, this g I x for a feature vector x will be computed for every ith class. Okay. And for whichever value of I the g I x is maximum, we put x or classify x to that particular class omega I. So, this is what we are calling as discriminant function. And we have also said that discriminant function g I x is not really unique. So, if I can identify any function f which is monotonically increasing, okay, then the functional f on g I x okay, where this function f, this is a monotonically increasing function. So, whenever this f is monotonically increasing, then f of g I x, that also serves the same purpose as discriminating function, because for whichever value of I g I x is maximum, it is for the same value of I, f of g I x will also be maximum. Okay. Then why do we put this functional f? It is only for convenience of application. In different applications, maybe g I x itself is not very convenient, but if I take a functional of g I x, then that may be more convenient for our application. Okay. So, coming to this particular case of Bayes minimum risk classifier or minimum error rate classifier, where we have said that our g I x can be the a posteriori probability p of omega I given x. Okay. Because as per our minimum error rate classification, it was 1 minus p omega I given x, because whenever this 1 minus p omega I given x has to be minimum, p omega I given x has to be maximum. Okay. So, I have to put this x into the class omega I for which p omega x is maximum. So, this itself I can take as my discriminant function g I x. Okay. And then we said that logarithm being a monotonically increasing function. So, I can also define g I x as log of p of omega I given x, and because p of omega I given x this is nothing but p of x given omega I into p of omega I upon p of x, okay, where we said that p of x we can remove, because for every value of I, p I x will always appear in the denominator. So, that does not really give you any discriminating power. So, I simply put this p of x given omega I into p of omega I. So, over there this function will be expanded to ln log of p x given omega I plus ln p of omega I. Okay. So, this becomes our discriminant function to be used for classification of an unknown sample x into one of the classes or one of omega i's. Okay. So, naturally here you find that because the probability density function is involved or the a priori probability is involved. So, the structure of this Bayesian classifier will depend upon what kind of probability density that we are making use of. Okay. So, we can have various types of probability densities, we can have normal density, we can have Laplacian density, we can have exponential density and so on, or Poisson density. Okay. So, depending upon what kind of density we make use of, or for a particular application what kind of probability density function is more appropriate, according to that our structure of the classifier will be different. Okay. So, the most common probability density function which is in use is the normal or Gaussian density, or okay. So, this is the most common probability density function, right. So, this normal or Gaussian density for a single variable case is simply given as p of x is equal to, as all of you know this expression, square root of 2 pi into sigma exponential minus half into x minus mu upon sigma square. So, this is the expression for normal or Gaussian density, where the mu is nothing but the expected value of x or mean value of x, which is simply given as integration of x p x dx, where the integral has to be taken over the limit minus infinity to plus infinity, okay. And sigma square, which is the variance, or sigma, which is the standard deviation, is simply given by the expectation value of x minus mu square, okay, which is nothing but integration x minus mu square p x dx. Again you take the integral from minus infinity to plus infinity. Okay. So, this is what is the expression of the normal or Gaussian density in a single variable case. Okay. And you find that this particular probability density function is specified only by two parameters. One is the mean value mu, other one is the standard deviation sigma or the variance sigma square. So, if I know only the mean value or the variance, then I know that what is this probability density function. Okay. So, in short, this PDF, normal PDF, is also written as n mu sigma square. So, which means that it is normal density with the mean value of the variable as mu and variance of the signal as sigma square. Okay. But we are talking about feature vectors, that means multiple number of components or multiple number of features. So, a normal density of single variable is not much useful for us, but what is useful for us is multivariate normal. Okay. So, let us see that what is that multivariate normal density. So, here instead of a single feature x, we have a feature vector, okay. And the feature vector is, again we use it as x, but instead of writing in lowercase x, we write in capital X. Okay. So, this p x in this case for a multivariate case will be simply given by 2 pi to the power d by 2 Okay. So, this is the expression for the multivariate probability density function, okay, where x is the feature vector, a variable representing the feature vector, mu is the mean vector. So, mu is nothing but as before the expected value of the feature vectors x, okay, where x is a d-dimensional vector. Because we have assumed that our feature vector is d-dimensional, that is d number of individual features are concatenated together to give you the feature vector. Okay. So, x is a d-dimensional feature vector. So, accordingly the mean vector mu will also be of dimension d. Okay. So, this 2 pi to the power d by 2, this d is nothing but the dimension of the feature vector. Okay. And this sigma is what is called the covariance matrix. So, as mu is the expectation value of x. So, as before, as in case of single variable case, we can write this as x p x dx, integral of x p x dx. Okay. And this covariance matrix, because this is the expectation value of the covariance of the different components. Okay. So, this sigma covariance matrix, it is nothing but expectation value of x minus mu into x minus mu transpose. So, you note carefully that it is not x minus mu transpose into x minus mu, in which case you get a scalar, because x is a d-dimensional vector, mu is also a d-dimensional vector. So, if I make it x minus mu transpose x minus mu, that becomes a scalar quantity or dot product of two vectors. Okay. Rather, it is x minus mu into x minus mu transpose. Okay. So, this becomes a d-dimensional vector. So, x minus mu is of dimension d by 1, because it is a column vector. Okay. And x minus mu is a vector or a row vector of dimension 1 by d, right. So, this is actually the outer product of two vectors, and when I take the outer product of two vectors, the result is a d by d dimensional matrix. Okay. So, when I take the expectation value of x minus mu into x minus mu transpose, what I get is a d by d dimensional matrix, and that is what is nothing but your covariance matrix. Expectation value of this is becomes the covariance matrix. Okay. So, as before, this can also be written as in the integral form x minus mu into x minus mu transpose p x dx. Take the integral of this over the limit minus infinity to infinity, then what I get is this covariance matrix sigma. Okay. Now, from here, if I try to compute what is the expected values of individual components. So, the expected value of the ith component mu I, which is nothing but expected value of x I, which is the ith component of our feature vector capital X. Okay. Similarly, sigma I, which is the ith component in my covariance matrix sigma, capital sigma. Okay. Sigma I, this will simply become expected value of x I minus mu I into ijth component, let us make it more general, sigma ijth component in my covariance matrix, that will simply become expected value of x I minus mu I into x j minus mu j. Okay. So, you find that what is the variance when I take these two different components x I and x j, that is what it gives you the covariance between the ith component and the jth component. Okay. And when I compute this sigma I j, which is an ijth component in my covariance matrix, that is given by this expression. So, obviously, if I make I is equal to j, that means sigma I, which are nothing but diagonal components, the components on the diagonal of the covariance matrix, that simply becomes expectation value of x I minus mu I square. Okay. And this is nothing but our sigma I square which is the variance of the ith component of the feature vector. Okay. So, when I talk about this covariance matrix, the diagonal elements in the covariance matrix actually give you the variance of the individual components of the feature vector, and the off diagonal elements ijth element actually give you the covariance when I consider the ith component and jth component of the feature vector together. Okay. So, the covariance matrix is a more general form of the variance that we usually use in case of a single variable case. Okay. Now, what does this multivariate normal density or the multivariate Gaussian density actually tell you? Let us consider the case of the single variable normal density. So, I have P of x which is given by the normal density this, okay, with mean value mu and the variance as sigma square, right. So, this simply means if I plot this normal density, plot of the normal density will be like this. Okay. Where the peak is, so I put x along the horizontal direction and p x along the vertical direction. Okay. So, when I have this single variable normal density, this simply tells you that if you take the samples from the same population, okay, then how those samples are going to be placed, how those samples are actually distributed. Okay. So, this distribution shows that most of maximum of the samples will be around this mean value mu, okay, and the other sample values will be distributed according to this. As you go away from the mean value, the population density will go on decreasing, and there are certain limit after which I can actually neglect the population density, which is given by say plus minus 2 sigma. Okay, that is the twice of the standard deviation on this side as well as on this side. If I go beyond that, I can actually neglect the population density. Okay. So, this is what is meant by this normal density function. Okay. Now, its interpretation in the multivariate density case. Before I go to this d dimensional case, let me just see what will happen in a 2 dimensional case, that is bivariate normal density, that is possibly you are asking in the last class yesterday. Okay. So, suppose I talk about only 2 variables x and y, okay, or I talk about the normal density of a vector x where this vector x has only 2 components, x 1 and x 2. So, this is a bivariate normal density. More generalization of this is multivariate normal density. Okay. Now, coming by the same expression, you will find that in such bivariate normal density, this expression as we have written in case of multivariate normal density, that is this. Okay. This expression can be simplified for a bivariate normal density. It is not simplified if I simply expand this exponential term, assuming that this x has only 2 components, x 1 and x 2. Okay. So, by considering that, this p x when x is 2 dimensional will simply be written as 1 over 2 pi. Okay. Now, value of d is equal to 2. So, d by 2 becomes 1. Okay. So, 1 over 2 pi into sigma to the power half. When I say sigma within modulo form, it is nothing but determinant of the covariance matrix. So, this modulo means it is determinant of the covariance matrix, because I cannot take square root of a matrix. Okay. However, I can take square root of a determinant, because determinant has a value. Okay. Matrix does not have a value, matrix has to be interpreted. Okay. So, this into exponent of again minus half, okay. Then this term x minus mu sigma inverse into x minus mu transpose sigma inverse into x minus mu. This can be written in the form, now I have two components, one is x 1, other one is x 2. So, x 1 minus mu 1 upon sigma 1, okay, whole square plus x 2 minus mu 2 upon sigma 2 whole square. This is a simplified expression, because I have assumed that the components x 1 and x 2, they are statistically independent. Okay. So, that is why I could have a simplified expression only in terms of sigma 1 and sigma 2, only the diagonal elements in my covariance matrix. Okay. It is only because my assumption that x 1 and x 2 are statistically independent. So, sigma 1 2 or sigma 2 1, they will be equal to 0, because x 1 and x 2 are statistically independent. If they are not statistically independent, then in this exponential term, I will also have terms corresponding to sigma 1 2 and sigma 2 1. Okay. So, for explanation, let me simplify, let me have a simplified assumption that as if x 1 and x 2, they are statistically independent. However, x 1 component has a mean value of mu 1 and x 2 component has a mean value of mu 2. That means, my mean vector mu is nothing but mu 1 mu 2, okay, and the covariance matrix sigma is nothing but sigma 1 square sigma 2 square 0 0. Okay. So, this is my covariance matrix and this is the mean vector. So, what is the physical interpretation of this particular bivariate normal density function? Let us draw this 2-dimensional space or 3-dimensional space, because x 1 x 2 are two axes of the sample points and the density function is p x, which is the third dimension. So, let me draw this third dimensional space. So, I put x 1 along the direction, x 2 along this direction and p x along this direction. Okay. Suppose mu 1 is, or the mean vector mu is somewhere over here. Okay. So, if mu is at this position, so that means the components this is the location of mu 1 and this is the location of mu 2. Is that okay? Now, find that if I break this expression, this term exponential of minus half x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square, this is actually product of two exponential terms. Okay. Exponential minus half x 1 minus mu 1 by sigma 1 square into exponential minus half x 2 minus mu 2 by sigma 2 square. Okay. So, when I consider, forgetting this part, exponential minus of x1 minus mu 1 by sigma 1 square. This is actually a normal density along x direction with a mean value at mu 1 and the variance sigma 1. When I consider only this component, exponential minus half x 2 minus mu 2 by sigma 2 square, this becomes a normal density along x 2 direction with mean value mu 2 and standard deviation sigma 2. So, this overall exponential term is actually a product of two normal density functions or two Gaussian density functions, right. So, if I plot this in this two dimension, okay, I will have something like this. I will have a peak of the density around this mean value mu, okay, mean position mu, and the densities will be, I will have Gaussian along this, okay. I will also have Gaussian along this, okay. And if it is a single Gaussian, if I assume that my sigma 1, let me take a simplified case, that sigma 1 square is equal to sigma 2 square. That means the variance along x 1 and the variance along x 2, they are same. Okay. So, the kind of shape that I will have over here is, if I have a single normal density, so that single normal density profile you would rotate around the vertical axis. So, whatever surface it will trace, that surface will be the surface of this probability density function P x, right. So, if I plot over this thing, the surface will be something like this. It will go on this side, it will come like this, of this form. Okay. Now, given this surface of this bivariate probability density function, if I now try to trace the loci of points of constant density, that means all those values of x for which P x is constant. Okay. So, those loci will be nothing but circles. Something like this, because along this value of P x will be constant. Okay. So, if I take the footprint of these loci on this x 1 x 2 plane, so on x 1 x 2 plane, I will have a number of concentric circles like this, where these circles, each of these circle represents the loci of points having constant density. As I move inside the circle, move towards the center of the circle, this loci or the density value of the density will increase. As I move away from the center, the value of the density function will go on decreasing. So, that indicates that along this circle I have the more probability of occurrence of the set of points which are drawn from a single population arbitrarily, okay, or drawing of one sample does not depend upon the drawing of another sample. Okay. What does it mean? When I simply take up the first object, I do not make use of any information of what was the previous object that I have taken. So, just blindly you go on taking the samples from a population and then the points will be distributed in this form. So, this is a simple case that I have taken when sigma 1 square is equal to sigma 2 square. That means, the variance along x 1 dimension and the variance along y 1 x 2 dimension, they are same. What happens if the variances are different? So, in that case, this circle will become ellipse. Okay. So, this circle that I have shown, when I have say sigma 1 square is not equal to sigma 2 square. So, one will be greater than the other. So, when sigma 1 square is equal to sigma 2 square, I had the footprints of the loci of the points of constant density as circles. Now, the loci of points of constant density will be ellipses. Okay. And how those ellipses will be formed? Something like this. So, this is a case when sigma 1 is greater than sigma 2. That means, the spread of points along x 1 axis is more than the spread of points along y 1 axis. If sigma 2 becomes greater than sigma 1, that is spread of points along y 2 axis is more than spread of points along x 2 axis is more than the spread of points along x 1 axis, then I will have the major axis aligned towards x 1 direction and the minor axis aligned towards x 2 major axis along x 2 direction and the minor axis along x 1 direction. Okay. So, this is the nature of the loci of the points of constant density, when my assumption was that different components of the feature vectors are statistically independent. That means, sigma I j was equal to 0 for I not equal to j. Okay. What happens if sigma I j is not equal to 0? That means, the samples are not, or the components of the feature vectors are not statistically independent. Okay. So, over there I will have my covariance matrix sigma. In this case, covariance matrix is a diagonal matrix, where only the diagonal elements are non-zero elements, all the off diagonal elements are zeros. Okay. If the components are not statistically independent, then even the off diagonal elements will also be non-zero. So, I will have a situation that sigma 1 square, sigma 2 square, here I will have sigma 2 1, here I will have sigma 1 2, where sigma 1 2 and sigma 2 1 they are non-zero values. Okay. So, if it so happens, here you find that the major axis and the minor axis of these ellipses, they are aligned along x 1 dimension and x 2 dimension. In this case, when the components are not statistically independent, then the directions of the major axis and minor axis of the ellipse will be given by eigenvectors of this covariance matrix. Okay. And the lengths of the major axis and minor axis will correspond to the eigenvalues of the covariance matrix. So, instead of having a footprint of the point of the loci of points of constant density like this, the footprints will be something like this. Again, it will be centered around mu, but the directions of major axis and minor axis will be given by the eigenvectors of this covariance matrix, say E 1 and E 2. So, this is my x 1 direction, this is my x 2 direction. Okay. And as I said that these directions actually tell you how the points are distributed. I will have maximum density along the around mean. As I move along this direction, the density will go on reducing. As I move along this direction, the density will also go on reducing, but here the rate of decrease of the density function will be more, here the rate of decrease of the density function will be less. Is that okay? Now, what happens in case of multivariate normal density? I have taken the example of bivariate normal density, but because still up to 2 variables I can visualize. The moment, so you consider the case from 2 variables, I go to 3 variables. So, I will have 3 axes, one corresponding to x 1, one corresponding to x 2 or the one corresponding to x 3, and I have to have a fourth axis which corresponds to p x, the probability density function. Okay. I cannot draw it on a 2 dimension of plane. Up to 2 dimension I can easily draw. When it goes to 3 dimensions, still I can draw, but with some difficulty. The moment it goes beyond 3, I cannot draw it on a 2 dimension of plane. Okay. But I can think of how the nature can be. Okay. So, when it becomes more than 2 variables, that is for multivariate normal density or for multivariate Gaussian density, again if I draw the sample of points from that multidimensional space, the points will form point clouds. Here also the points are forming point clouds, okay, or clusters of points, where the maximum density will be around mu 1 or around mu. As I move away from mu, the density of the points goes on reducing. Okay. When I go for this multivariate normal density, then also I can say that those multi-dimensional points will form point clouds, okay, in a multi-dimensional space in such a way that again around mu the density will be maximum. As we move away from mu, the density will go on reducing, and they will be clustered. Here this clustering is in the form of an ellipse. In multidimensional space, it will be an ellipsoid. Okay. So, the points will be clustered in an ellipsoid, right. So, again in 3 dimensional space, if I simply rotate this ellipse around a particular axis, I will have a volume. So, the points will be clustered in that volume. At the center of that volume, that ellipsoidal volume, the density of the points will be maximum. As I move away from the ellipsoidal volume, the density will go on reducing, again following that normal density function or Gaussian density function. Okay. So, over here as in this case, the loci of points of constant density forms ellipses. In multidimensional space, the loci of points of constant density, they form ellipsoids. Okay. And this ellipsoid will have a quadratic form, which is given by x minus mu transpose sigma inverse into x minus mu. Okay. So, this is the quadratic form of loci of points of constant density. Okay. And the principal axis of this ellipsoid, as in this case, the principal axis of the ellipses are given by the eigenvectors of the covariance matrix. So, in the same way, the principal axis of the ellipsoids in this case will be given by eigenvectors of the covariance matrix, and the lengths of the axis will be given by the corresponding eigenvalues. Is that okay? And this term, the distance function, actually this loci is nothing but the value of the distance values from the centroid, right. So, mu gives you the center of the centroid and x is the points lying on the periphery, and this term actually gives you the distance of x from mu. Okay. So, distance function r square I can define, which is given by x minus mu transpose sigma inverse into x minus mu. Okay. In Euclidean case, I can define d square is equal to x I minus mu I square, take the summation over I is equal to, instead of calling it d, let me call it say L. where I is equal to 1 to d, because we are assuming our vectors are d dimensional. Okay. So, this L square is equal to x square minus x I minus mu I square, take the summation from I equal to 1 to d. This is what is our Euclidean distance. Okay. This distance function, if I define as x minus mu to the power transpose sigma inverse x minus mu, this is what is called Moholy-Nagy distance. Named after the great statistician P.C. Moholy-Nagy. Okay. So, this is what is called Moholy-Nagy distance. No, square. It is a quadratic term, x minus mu transpose into x minus mu. The distance is r. The expression is given by this. That is quite obvious. Okay. So, now let us see that how this can be utilized. So far, whatever I have discussed is about the probability density functions, univariate case, bivariate case, multivariate case. I have not gone beyond that. But we started with that how these probability functions actually influence the structure of the decision surface. Okay. We started with that, because our g I x was ln p of x given omega I plus ln p of omega I, probability density and the conditional density function. Okay. So, we started with this. So, our purpose is to find out g I x, which is the discriminant function. Okay. So, as given, g I x is nothing but ln p of x given omega I plus ln p of omega I, okay, where the expression of this p of x given omega I, what is said is p of x given omega I means we are taking the samples from class omega I, finding out its probability density function. So, expression will remain the same. The mu and sigma will be replaced by mu I and sigma I. That means, the mean vector for the samples taken from class omega I, covariance matrix computed from the samples taken from class omega I. That is all. Expression will remain the same. Okay. So, the expression for the probability density function, if I write p of x given omega I, it is nothing but remains the same expression 1 over 2 pi to the power d by 2, okay. Then determinant sigma I to the power half. Okay. So, you find that sigma I have replaced by sigma I into exponential minus half, okay, x minus, now mu has to be replaced by mu I. This mu I do not put it as ith component of mu, rather this is the mean vector of class omega I. Okay. So, x minus mu I transpose sigma I inverse, okay, into x minus mu I. This is my probability density function or class conditional probability density function. Okay. So, by using this particular probability density function, multivariate probability density function, now I can define g I x to be logarithm of this term, okay, plus logarithm of p of omega I, that is the a priori probability. So, it will simply become, this is an exponential. So, if I take the logarithm, it will be simply this. So, it simply becomes minus half into x minus mu I transpose sigma I inverse x minus mu I. Okay. This becomes minus d by 2 logarithm of 2 pi. This term becomes minus half log of determinant of sigma I. Okay. So, all the terms of this expression are taken care, plus I have to put this term, which is log of a priori probability p of omega I. Okay. So, this is the expression for discriminant function corresponding to class omega I. Okay. So, from here you find that this is actually a quadratic expression, is it not? I have x minus mu transpose into x minus mu with sigma I inverse sandwiched between these two terms. So, actually this is a quadratic equation. So, Bayes discriminator is actually a quadratic discriminator in general, or when I want to compute the decision surface between two classes omega I and omega j, the decision surface will actually be a quadratic surface. It is not a linear surface. Okay. So, this classifier can take care of linearly non-separable classes. However, for specific cases, this can be converted to a linear classifier. So, we will talk about those things in the next class. Let us stop here today.